Today I'm excited to demonstrate our smart washing machine control system built on the ISP568 standard. What you're looking at is an intelligent fuzzy logic driven system that replaces rigid traditional wash cycles with dynamic sensor-based optimization. Instead of just guessing how long a wash should take, the system analyzes fabric type, weight and soil levels to calculate the exact amount of water and time needed. Without wasting any more time, let's launch our expert system. Now we are at Simulator and Graph tab. This page displays the academic presets for our smart washing system. Instead of manually entering all the washing parameters, users can choose from several predefined washing modes based on the types and condition for their clothes. For example, we have delicate wool, standard daily wash, dirty denim, quick refresh, and muddy spots here. Each preset automatically applies the appropriate fuzzy logic settings such as wash time, water level, agitation speed, and detergent amount, providing a faster, more convenient and user-friendly washing experience. Now let us move on to the Cribs sensor inputs. Our sensor inputs are set to a standard daily wash profile, a soil level of 60%, a load weight of 4.7 kg, and a fabric delicacy rating of 50%. Watch what happens to our fuzzy sets in Graph 1 when I actively adjust these parameters. As you guys can see, as I adjust the sliders, the system instantly performs fuzzification. It translates these raw percentages and weights into degree of membership. For instance, at 60% soil level, the machine recognizes the load as being 33% moderately soiled and 40% heavily soiled. Moving down to rule evaluation, out of 75 total rules in the knowledge base, the system identifies exactly which rules are active. Right now, 4 rules are firing. It uses the main operator for implication, clipping the output shapes. Then, let's look at Graph 2, results and clipping. It aggregates these shapes using the max operator. By calculating the center of gravity COG of this combined shape, the system defuzzifies the data into a precise real-world instruction. As a result, our live control output dictates exactly 27.65 minutes of wash time and 43.56 liters of water. So no wasted resources, no underwashed clothes. Now, let's transition to the Logic Report tab to see the transparent mathematical audit trail behind these decisions. In a production environment or an academic review, we can't treat AI as a black box. The Logic Report breaks down the exact formula used at every stage of pipeline. It explicitly lists the active membership functions, shows the precise clipping levels for every firing rules, and provides step-by-step summation for the centroid defuzzification formula. This ensures that every cycle executed by the hardware is fully traceable, mathematically sound, and auditable. Wrap up by combining the real-time adjustment of the simulator and graphs interface with the rigorous mathematical validation of the logic report, the system proves how fuzzy logic can make everyday appliances significantly more sustainable and efficient.
Today, we're putting on our business strategist hats to review a genuinely fascinating and highly viable commercial asset, the Smart Washing Machine Fuzzy Logic Control System. Throughout this explainer, we're going to meticulously break down the ISP568 standard project report. Now, our goal here isn't just to admire the impressive academic syllabus or the complex mathematical theory behind washing control systems. No, we want to translate this technical framework into a clear, hard-hitting strategic market value pitch. We're going to look closely at how the system operates, exactly who it serves, and most importantly, how it generates revenue.
So, let's jump right in. The central strategic question driving our whole analysis today is this: how exactly do we translate the ISP568 fuzzy logic standard into commercial market value? Think about it. How does an academic syllabus on fuzzy logic, a system relying on 75 complex mathematical rules to map soil levels, load weights, and fabric delicacy, actually engineer real-world profitability? To answer that, we have to bridge the gap between algorithmic theory and everyday consumer demand. We essentially have to prove that this technology solves real, quantifiable problems that people are more than willing to pay for.
To do that, we'll be critically evaluating 4 key pillars today: target markets and deficiencies, economic value and revenue, our strategic SWOT analysis, and finally, the product growth roadmap.
Let's start with Section 1, Target Markets and Deficiencies.
The entire foundation of this commercial pitch really rests on 3 core project objectives outlined in the report. First up, the system aims to make washing fully automatic. So instead of those arbitrary binary timers we're all used to, this system uses specific inputs, dirtiness, load weight, fabric type, to auto-calculate the exact wash time and water level. Second, it's designed to heavily save resources by aggressively adjusting its output based on that exact weight and dirtiness. And third, it actively aims to protect clothes. Because it takes fabric type as a direct input, it can be gentle on your delicates while staying incredibly tough on heavy stains. Now, these aren't just neat engineering goals, they are direct, targeted solutions to existing market failures. Notice how perfectly those engineering objectives map onto our 3 defined target user groups and their specific documented pain points. Take smart appliance companies, for instance. Their massive problem statement is wasting water and energy. Their fixed cycles just can't adapt to actual dirt or weight, and that really hurts their sustainability ratings. Then you look at everyday homeowners. Their biggest pain point? Guessing the right settings. They're constantly risking either wasting water on a tiny load or getting terrible cleaning results on a heavy one. Finally, we have laundromat businesses. Their huge liability is damaging delicate clothes or undercleaning heavy dirt simply because their machines rely on a one-size-fits-all washing approach. This fuzzy logic control system steps in and provides a beautifully tailored mathematical solution to every single one of these deficiencies.
Moving from market deficiency to financial opportunity, Section 2 covers economic value and revenue.
We've identified 3 actual revenue streams, and our first is B2B algorithm licensing. The strategy here is brilliant in its simplicity. We license the fuzzy logic control firmware directly to Tier 1 manufacturers. Think appliance giants like Bosch and LG. The stated pricing model secures the 6.50 Malaysian ringgit licensing fee per unit. The absolute key takeaway here is that this requires 0 heavy manufacturing on our end. It is a pure intellectual property play. By embedding our algorithm right into their hardware, these companies instantly upgrade their product lines to smart status, and we just sit back and collect a highly scalable per-unit royalty.
Our second economic stream pivots nicely to a software as a service, or SaaS, model targeting the B2B commercial sector, specifically through commercial retrofit kits. This generates a solid 90.00 Malaysian ringgit monthly subscription fee. Here, we're targeting those laundromat businesses we identified just a minute ago, upgrading their existing legacy machines via IoT retrofits. So, rather than forcing them into the massive capital expense of buying entirely new fleets of washing machines, they just pay a recurring monthly SaaS fee to optimize their current inventory. It's a win-win. They vastly reduce their water waste and dramatically cut down their liability for damaged clothes.
And the third economic pillar? That leverages government sustainability initiatives through green energy certifications. By integrating our system, which, as we know, drastically optimizes water and energy use, appliance manufacturers suddenly qualify for highly lucrative Malaysian GHIT and GITA green tax incentives, as well as carbon offset rebates. This isn't just a revenue stream for us, it's an incredibly powerful sales tool. We aren't just walking into an appliance manufacturer trying to sell a 6.50 ringgit firmware upgrade. We are actually selling them a direct, verifiable pathway to massive corporate tax incentives and environmental compliance.
To ensure a perfectly transparent pitch, Section 3 is our strategic SWOT analysis.
Let's start by looking at the internal factors, our strengths and weaknesses.
These really illustrate the classic trade-offs of advanced engineering. On the strength side, we've got non-linear control that seamlessly adapts to dynamic soil loads. We boast mathematically verified resource savings of up to 35% in water and energy, and we actively preserve fabrics compared to that aggressive timer-only washing style. However, those strengths do create some weaknesses. We're inherently dealing with a higher design complexity versus simple binary timers. Plus, the system's efficacy is heavily reliant on exact sensor calibration. If the input parameters for load weight or turbidity are slightly off, the fuzzy logic rules will inevitably output the wrong wash duration and water level.
Looking outward to the external market conditions, though, the opportunities heavily outweigh the threats. The opportunities include massive expansion potential into smart home integration ecosystems. Think Apple HomeKit and Home Assistant. There's also clear, logical scalability into industrial dishwashers and broader commercial laundry applications. And honestly, rising global water and energy compliance demands act as a massive tailwind for this kind of technology. Now, against all of that, we do face two main threats: the ongoing presence of low-cost binary timer competitors who can easily undercut smart appliances on price, and the very real risk of supply chain volatility for the exact weight and turbidity sensors our complex system relies on.
Finally, let's examine Section 4, the Product Growth Roadmap. The engineering and deployment progression here is strictly defined across a 3-phase execution timeline. We move from Phase 1, our current status, into a 6-month milestone for Phase 2, and then culminate in a 12-month milestone for Phase 3.
Let's break down how this builds step by step. Phase 1, right where we are currently, centers entirely on mathematical simulation. This is hosted on a web platform verifying our 75 distinct fuzzy logic rules and validating the center of gravity, or COG, outbounds for wash duration and water level. Once that logic report is totally perfected, Phase 2 hits at the 6-month mark, shifting us to the embedded hardware prototype. This transitions all that beautiful math into the physical world using an ESP32 microcontroller paired up with analog weight and turbidity sensors. And finally, Phase 3, at 12 months, scales us right into IoT edge analytics. This enables Wi-Fi over-the-air or OTA calibration, which directly mitigates that sensor reliance weakness we just talked about in the SWOT, and introduces mobile dashboards for commercial utility monitoring, fully enabling that 90 ringgit SaaS revenue model we discussed.
I want to leave you with this final quote, which I think perfectly represents the core ethos of this entire project report: a system that thinks like a human brain to save resources and protect assets. By applying 75 meticulously calculated rules based on load weight, soil level, and fabric delicacy, the ISP568 standard essentially mimics human reasoning biologically. We've seen the very distinct user pain points it solves, the exact ringgit value revenue models it unlocks, and the highly strategic roadmap it follows. So the real question to consider as we wrap up is this: as global resource compliance inevitably tightens, can any appliance manufacturer out there truly afford not to integrate machinery that thinks before it acts?